So how many loops do we need? We need 2 loops. So we need a voltage loop. So how can we do the voltage loop control? First, we need to know the reference. So this could be 400 volt. And we compare the output and the reference. So we use reference voltage minus output voltage. So this is error. So we have error here. Then we design PI controller. So PI controller here. So sorry, we have reference, we have output, we have error, and we design PI controller. Then we obtain V control. So here is V control. And then we use a multiplayer to multiple V control and VGT. So here we sense VGT. So this is VGT. Here is our V control. And then we can generate V reference. So this is V reference. V reference is equal to IG star. So this is desired IG. So what is IG star? So we have VG here. This is VG. What is IG? IG should have the same shape with VG. So this is IG star. So we use V control synchron, and we use VGT to generate IG star. So we call this is voltage loop control. So voltage loop control use feedback voltage to generate IG star. Okay. Then we have to design current loop control. What is current loop control? We input desired current. So desired current is IG star. Here, IG star. Then we have to compare desired current and the real current. So we feedback the real current. So we feedback the real current. So this is desired current. Input here, and we feedback IG. This is real current, right? And then we can create current error. Right, current error. And then we have to design PI controller. So we have to design PI controller. And we can generate the error synchron. So this is control U for current. But the control U should change to switching. So how can we have a linear value control to on-off value? You have to use what? PWM, right? We mentioned before. So then you have to compare the PWM synchron. So we have control synchron here. We have PWM synchron here, right? We can determine on and off. So we mentioned this before. We call this is current regulated. So this method is called current regulated. We try to regulate the current to follow the current command. So this is current regulated. So we have PWM, then we compare the control synchron and the PWM. Then we can generate 1 or 0. So if this is positive, then we can turn on the Q1. If this is negative, then we can turn on the diode. So if we turn on the diode or Q1, then we we can generate current. So we have current IG star. So you can see we can turn on Q1 or turn on D1, but then we can change the current. And then the current feedback. So we call this is current regulated. So how many loops do we have? Totally how many loops? Voltage loop and what? Current loop. So you can see this is current loop here, current loop. How about this one? Voltage loop, right? This is only for this stage. What is this stage? PFC, right? How about the next stage? You have another buck converter. You have another reference. This is 5 volt because this is your cell phone. And reference is 5 volt. This is real voltage, 4.5 volt. Then you have 0.5 volt difference. Then you design PI controller to control the buck converter duty. So how many stages do you have? 2 stages. So you have 2 stages. One stage is PFC stage. Another is buck converter stage, or the output voltage regulation stage. So you have 2 stages. Then you report your idea to your boss. You say, oh, now I developed a perfect PLC. I have 2 stages. So this is for cell phone voltage regulation. This is for 400 volt regulation. So the 400 volt include the voltage loop control and the current loop control. And your boss say, oh, this is a great idea. But how many devices you use extra compared to the traditional one? What is the traditional one? We have rectifier. We have AC input. We have rectifier. Then we have huge capacitor, right? After the huge capacitor, we have DC-DC converter. So this is 150 volt DC. Then output is 5 volt. So we have DC-DC buck converter. Then we have small capacitor here. We have resistance here. Do we need a feedback here? Yes or no? Do we control this voltage? No. Right? Do you control this voltage? No, you use huge capacitor. Then you don't do anything, right? And you only control this one. So what is this voltage? The voltage is like this. But it is okay. I don't care. I don't care. So now you design this circuit. My question is, how many devices do you use actually? You use a multiplayer. This one IC, multiplayer integrated circuit, analog integrated circuit. You have OP for comparison, right? So you have comparison, maybe for OP. You have small resistance, right? So RS. You have PWM here, PWM. You need a PWM. You need controller, right? How can you design controller? Use operation amplifier to design PI controller. Okay, then you finish. So this is first one. And also you need to trigger. So you have triggering, we call driver. maybe an optical driver here. And then you also need to sense the voltage. So you need voltage sensor here. And then what do you need? Comparison, right? Reference and the output. You need comparison. And what do you need? You need voltage PI controller. You need PI controller. And then you also need a compensator here, right? So you need load compensator, load PI. And then you also need to know the output voltage of load, right? So you need a comparison for the load. So your boss will ask you question, how much money do you spend? So totally, how much money do you spend? Maybe you say, I need 1,500. How about the original one? This one, 500. How much cost do you increase? 4 times, right? So do you like to do this? So we say this is good, but do you think it is cheap? It is not cheap. You need a lot of sensor. You need a lot of IC, multiplayer, PWM. You need a PI controller. You need a driver. A lot. Can you merge this one and this one to become one stage? So for this one, what is the purpose? To regulate the output voltage. For this one, regulate the output voltage and the input current, right? They have their own purpose, their job. Can I combine this one and this one to become one stage? So can I read a paper and give a lecture at the same time? No, you will interfere each other, right? So the answer is very hard. But I need to reduce my cost. So some people propose, yes, we can do this. But if we do this, we have to reduce our performance, right? Maybe I have 1 hour and I spend half hour to read paper, half hour to give a lecture, but I reduce my performance, right? Then it is fine. So can we do this? Yes, we can. So some people propose one stage PFC. For what purpose? Reduce cost. So this is one way. And your advisor will ask you another question. Can you reduce your cost? Because it is too cheap, too expensive. The industry cannot accept this one because original 500. Now you tell your user you have to spend 2,000 to buy a charger. Your customer say, oh, it is too expensive. I only need a charger. I don't care about the input current, right? But then you cannot sell in some country. So your boss still asks you to finish your job in a low cost. So what can you do? So this is a challenge. So how can you reduce the cost but still get PFC? So this is a good idea. We have AC voltage, we have VG, then we create IG star, then we use current regulated to follow the IG star, then we go back to the AC side. We have pure sinusoidal AC voltage and very close to pure sinusoidal AC current. And the phase angle phase difference is 0. So it is perfect idea. But to implement the circuit, we need a lot of sensor and a lot of IC. And we increase the price to 4 times. Then the user say it is too expensive. I don't want to spend 1,500 for buying a power factor. It is not my business. I only care about my load side, right? So what can you do? So some people propose another idea. So what is the idea? Because we use too much device, we use too much circuit. So I need to reduce the circuit to simplify the circuit. So what can I do? So I change my idea a little bit. So we still use rectifier. So we use rectifier. And we still have VG. And we have AC voltage. So the same. We have AC voltage. And we have AC current. So I still hope the AC current can follow the AC voltage. The same idea. But I don't need a multiplayer. I don't need a PI controller. I don't need feedback. So what can I do? So I use switch here. Then I use diode here. Then I have output capacitor here. Okay, output capacitor here. Then I have load here. And also I can design a buck converter. This is DC-DC buck converter. Then I can get 5 volt here. Very similar to before. So this is my idea. But I don't like feedback. I hope I don't need feedback. So what can I do? So I can turn on the switch. If I want to increase the current, I just trigger the switch. If I trigger the switch, then this becomes 0 voltage. So this is 0 voltage. And we put small inductor here. So we have small inductor here. We have small inductor here. And we have small capacitor here. And a small inductor here. So if I turn on the switch, then I have here, I have VG. The VG is like this. But we have AC, but we go through the inductor. So then we can say VG equal to twice of the small inductor. And then dI/dt plus here is 0 volt, right? Because short circuit. So if I short circuit, I have inductor here. Then what is the current? So dI/dt is equal to, how can we say this? This is L, this is L. And then we have VG divided by 2. And here is 0. So now VG is positive here. VG is positive. So this is positive. And positive divided by 2 is also positive, right? And L is inductor. It could be small inductor, 1 millihenry. It is positive. This is positive, this is positive. How about this one? Positive. If dI/dt is positive, how about IT? IT is I0 plus L VG2 multiplied by delta T, right? You can solve this equation easily. So what is your current? If you have positive voltage, what is your current? Your current could be like this. this current. So I use discontinuous. So when I reach 0, then I turn on again. So I have turn on again, then turn on again. So I have this kind of IG. Here I have this kind of IG. So every time I have to make sure the current reach 0, then I can turn on again. So my current becomes this, on, off, on, off, on, off. So I wait a small time. Then I can get this current. If I can get this current, so the average is like this. Average is like this. So I can get input. How about input? Input we have VAC like this. How about our current? Our current like this. So if I take the average, it is like this, right? So I have a near sinusoidal current like this. And then I have a filter here. So after the filter, my current could be like this. Could be like this. So I get a near sinusoidal current here. The current is not good. The current is not as good as before. But it is still sinusoidal. And 0 degree phase shift. I still can use it. But what can I remove? I can remove how many? Multiplier, comparator. So I wait until the current reach 0. Then I turn on again. So I can calculate how much time do I need. So I use a timer to decide when should I turn on, when should I turn off. So I don't need any comparator. So I don't need RS. So we don't have any RS. We don't need any PWMIC. We do not use any PI controller. No feedback. We still need trickling driver. So we do not have the voltage sensor, the output voltage, no sensor. We do not need output comparison. We don't need output PI controller. The load is the same, we still keep. So we remove a lot. So the performance is worse. But if it can pass, then it is okay, right? So what is your purpose of PFC? I only need to pass the regulation. That's all, right? So if I can pass the regulation say your PFC at least 0.9, but now I reach 0.91, then I'm fine. So if you have if you want a happy life, so what can you do? You can sleep every day, 10 hours. You can have Saturday and Sunday go outside to enjoy life. So you need only study 6 hours per week, but finally you get a B. It is not good, but I still graduate. Then I pass the law, right? So this is PFC. I don't need to reach 4.3. I only need 3.5. So I can have a happy life. So this is the idea of the PFC. So we can design this circuit. It is much simpler than before. Then you can get patent. Then you can pass. Then you can get a paper. Then you can graduate tomorrow. Do you like this? Yes, I like this. So this is another idea people propose to use for the PFC, especially for the low load PFC. Maybe only 100 watt or less than 100 watt. How about 3 phase? we can use the same idea. So three-phase, we do not need to feedback. So we do not need to control. So we only turn on, turn off, turn on, turn off. Then we can get unity power factor. We can use the same idea. Then we can save a lot of money, but the performance is not as good as before. So we also can apply for the three-phase PFC. So this is the fundamental idea people propose. So do you have another one? You can say, yes, I can propose another one, and I will submit a paper, I will submit a patent, some company will buy my patent, some company will hire me, then I can graduate next month. So you have to calm down and think about it, right? Because currently, people propose two ideas. Okay? So, we also can propose this one. So this is LC, and we have three-phase here. And we use only one switch. So we have three-phase, VA, VB, VC. So we have VAN here. And then we control the current like this. And we have VBN here. Then we can control the current like this. So then we have three-phase, but only one switch. We only need one switch. This is also okay. So this is discontinuous mode. We also can use this, but it should be very low power. We cannot use for high power. Why cannot we use for high power? The reason is like this. If you have a current here I need 10 ampere. But now you use discontinuous. What is the peak? More than 20 ampere. And your current increase quickly, decrease quickly. Then you found if some friend in the lab work with you, then their equivalent doesn't work because this current change too quick. And you broke everything. Then your computer failed because your power quality is not too good. So you can see this is not good. So do you like continuous current or do you like discontinuous current? Should be continuous, right? Because this one, you change too quick. Then your power quality was influenced. Then if you use computer, if you use oscilloscope, they don't work. They fail. So this is the problem. So also it can be used, but it still has some disadvantage. So the current is like this. So how about phase control? If we have MRT system, if we have elevator, what can we do for power factor correction? Then you can say we have AC input. AC input. So we call this is SCR, 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 SCR. We can control the delay angle. So we trigger the SCR for T1 and T4. And we trigger the SCR for T2 and T3. Then we can get the output voltage like this. So if T1 and T4, then we have current go this way, positive. So this is positive. If T2 and T3, we have current go this way, then the current become what? Negative, right? So this is negative. So you can see the input voltage and the input current. So now we remove the diode. We use the SCR because this is thyristor SCR. If we use HDR, we can control the delay angle. So now we have input voltage here, but we trigger here. So we delay 30 degrees. Then what is VA? Then the VA become this one. So here we can get. So this is output. We call this is VA. And how about the input current? The input here, input current here is positive, here is negative. So we have input current here. Then if we compare input voltage and the input current, then what is input voltage here? This is V in. What is input current? The delay 30 degrees. So this is positive current. This is negative current. So something like this. So then we can use Fourier series to find that the fundamental is like this, right? And the voltage is like this. So what is the phase delay? This is sine wave current. This is sine wave voltage. So the phase delay is how many degrees? 30 degrees, right? The current lag voltage, how many degrees? 30 degrees. So if this is 30 degrees, what is cosine 30 degrees? 0.866. So do you think that your power factor can be increased or decreased if your firing angle is delayed? It is decreased. For example, if you become 60 degrees, then it becomes 0.5. If you become 90 degrees, it becomes 0, right? So the more delay, the worse of the power factor correction. So before we use DC motor, we control the DC motor. And then if we control the DC motor at a low speed, then the power factor becomes more poor. If we control the DC motor for high speed, then the delay angle is small, then the power factor is higher. So when we control the motor, the power factor is always changing. So this is phase control rectifier. So what can we do? We can use inductor to replace capacitor. So before, here we use capacitor, but now we use inductor. If we use inductor, then the current is close to sinusoidal current, then it could be better. If we use the capacitor, then the current is like this, then it is not good. But now it becomes square wave, right? It is better. So we can compute the power factor. It is 0.9 multiplied by cosine alpha. Alpha is the delay angle. If alpha is 0, then the power factor is 0.9. If alpha is 30 degrees, then what is your power factor? 0.9 multiplied by 0.866. So it is almost 0.86. So it is not bad, but it is also not too good. So we can adjust alpha, and we can obtain different power factor. However, if we adjust alpha to 90 degrees, the power is 0. If our delay angle is larger than 90 degrees, then the power is negative. So can you explain what is negative power? If you control the alpha more than 90 degrees, then your load can receive negative power. What does this mean? Your load receives minus 5 watts. What does this mean? Means your load supply 550 watts into the power system. So we call this is regeneration. You return your power into AC side. So we call this is regeneration. So if you have elevator, so you have elevator here. This is some iron. This is your cage. So if you falling down, then you can find the speed is quite quick, and then you can return your power into the power system. So you give power to your power system. Then Taiwan Power Company should pay you money. Then you save a lot of energy and then save a lot of money. If you have an MRT car, when the MRT come here, it need a lot of energy from power company. But when it reach the station, it reduce speed, then the MRT can provide energy to power company. Then the power company should pay money for the MRT system. What does this mean? This is energy regeneration. So they create energy. So if we control the motor, sometimes we have to get the energy from the source. Sometimes we can supply energy back to the source. Then the Taiwan Power Company should pay you money, so you can save energy. Okay, so we can see here. So we call this is HCR. So this is diode, but if you use this symbol, it becomes HCR. So what is HCR? 3 terminal, anode, cathode, gate. For diode, if this is positive, this is negative, you should turn on. For HCR, you have to use the trigger signal to trigger it, then you can turn on. So this is gate control. If you have a trigger signal, then the voltage can come from anode to cathode. Then we call this is silicon control rectifier. So if we have a gate signal, then it turn on. If we do not provide gate signal, it is always turn off. So once it's turned on, it always turn on. How can you turn off the HCR? You have to put a negative voltage in anode and the positive voltage in cathode. This is the only way, but it is very hard to control. So this is HCR. Okay. Okay, so now I will show you something. Okay, this one. So sometimes we have a motor here. We have HCR 1, 2, 3, 4, 5, 6. Then we say we can turn on T1 and go back from T5. So T1 turn on, T5 turn on. So we can say we have T1 turn on and T5 turn on. So we have T1 turn on and T5 turn on. So T1 and T5. So T1 turn on and T5 turn on. So we go from A to B. So V, A, B have a loop. So then next, we want to change. So before it's T1 and T5. And next time, we could turn on T3 to replace T1. So here, we want to turn on T3, but we still want to turn on T5. So it is like this. So first, T1, T5. Next, T3, T5. So before, it goes this way, T1, T5. So AB, then T1 and T1, no, before it's T1, T5. Next time is T3, T5, right? So for SCR it is quite slow. So if you turn off it, it not immediately turn off. It causes some delay. Okay. If you turn on this one, it also causes delay. Then what happened? Here, T1 still turn on. T3 try to turn on. Then T1 and T3, what happened? Short circuit. So you can have T1 and T3 short circuit. So which means A and C short circuit, right? What is the voltage between A and C? It is 220 volt multiplied by square root of 3. So maybe 380 volt short circuit. Then what happened? We create a huge current here, right? Because short circuit. So we call this is overlap. So they have overlap because the SCR is so slow. Once you ask him to turn on, he cannot turn on immediately. Once you ask him turn off, it cannot turn off immediately. So they cause overlap. If they overlap, then what happens? It is like this. So now we have A go here. Before we go back from B, next time we want to go back from C, but B not turn off. B not turn off, C already turn off. Then B and C short circuit. Then you can see we have I0 here. Then the I0 go I5 and go I6. So I0 is equal to I5 plus I6. If we take the differential, dI0 dt is 0. Because I0 is constant, the differential of constant is 0, right? And here we have dI5 dt plus dI6 dt. Then we can multiply by the leakage inductance. LL dI5 plus LL dI6 equal to 0. So 0 multiplied by LL still 0. So we can say we have Vx here. Vx is Vb plus this voltage drop. Vb plus VL LdI5 dt. And Vx also here. So Vc plus LL dI6 dt. So if we summation this one and this one become 2Vx, this one and this one, Vb plus Vc plus twice of L dI5 dt and LL dI6 dt. But dI5 dt plus dI6 dt is 0. So here is 0. So then Vx equal to 0.5 Vp plus Vc. So what is this voltage between Vp and Vc? Half Vp, half Vc. So then what happened? Vp and Vc short circuit. So if you put Vp and Vc short circuit, then you create a huge current. So we can see the waveform. So before we have this voltage, but now Vp and Vc become 0.5 Vp plus Vc. Then the voltage change to this waveform. So our voltage before is like this, but now it changed to like this. So we miss this part. Then what happened? The voltage changed quickly. Then it creates a lot of EMI to influence your facility. If you use a computer near this circuit, then your computer doesn't work because DVDT, the voltage change quickly. Then it's like an antenna radiation. So the voltage influences your computer, then your computer fails. And the voltage influences the light, then the light quickly. So sometimes turn on, sometimes turn off, then burn out. So you can see, we call this is power quality. So your power quality become very poor. So how can you solve this problem? So you can see your line voltage become this one. Notch, and a spike. Your current is like this. So your voltage is not pure sinusoidal. Your current is not pure sinusoidal current. Then what can you do? You have to design filter. So you have DVDT. So if you have a circuit to detect the zero voltage, then you have a lot of zero voltage noise. Then you have no opportunity to precisely detect the zero voltage. And you create DVDT. Sometimes it becomes resonant and it becomes series harmonics to other utility. So your computer, your UPS, your cell phone always fail. So you have this kind of problem. So what can you do? You have to design passive filter. So now we have to design filter for I5, I7, I11, I13. So you need to design filter to trap the harmonics. Okay, so you create a lot of utility problem. Your power factor become poor. You have voltage notch, they jump quickly. You have series harmonics current. Then you need to design some filter to remove this kind of problem. So in general, if you design a new system like high-speed train, or you design a new system for high-power steel company, it is easy to create this kind of problem. And you have to pay a lot of attention to improve it. So now, in this chapter, we discuss about rectifier. We discuss about single-phase rectifier. So what is the problem of single-phase rectifier? The current is good. The voltage is good, but the current is not good. We have this current. So we call this current has a huge harmonics and a poor power factor. So if you analyze, the current is not close to sinusoidal. So then your product, your charger can be used, no problem. But some company set some law to regulate the input harmonics and the input power factor. If you cannot fit the regulation, your product cannot be sold in this company. So what can you do? You need to design a PFC. So this is the original idea of PFC. So although you can design two-stage PFC, you can design very complicated circuit to improve the power factor, but the cost become 4 times. Then your boss say, I cannot pay this because my product cannot compete with other companies' product. Your price is too high, right? So what can you do? You have to use your own brain to simplify it, to design a simple PFC. And we discussed about AC-DC converter. So for AC to DC, in general, we need a two-stage. The first stage deal with the PFC. The second stage deal with the load voltage regulation. So we need a two-stage, and we need a lot of control, a lot of feedback. Then our price become very high. So this is the problem. So how can you combine the two stages into one stage? So this is your value. If you can do this, you say, oh, I can get 0.19 power factor, but my price only increased 10% when I compare to the traditional rectifier, then your boss will be very happy, right? So your circuit can apply for pattern. You can get the intelligent property. So everybody try to do this, but this is not easy, because from the principal point of view, if I want to give a lecture and I also want to make a phone call, can I do these two things at the same time? The answer is no, right? Because you will interrupt each other. So you have load side, you have PFC side. Can you combine PFC and the load side? In general, you need to use your own brain to think a compromise way, right? So this is the challenge. If you can do this, then you can have a PhD degree tomorrow, and you can apply for a patent tomorrow, and you can get a job tomorrow, and your idea can become a product tomorrow, then you can become the richest person in the whole world. So do you like to do this? Yes, right? So this is good opportunity. So we discussed about single phase control converter. We also discussed about a three-phase converter. So we avoid to use control. We avoid to use feedback. So what can we use? We try to use discontinuous mode. However, if we use discontinuous mode, the current ripple become very serious. So in this case, can you apply this idea into high power? The answer is no, because you have 20 ampere go up and then jump to 0. Then you create EMI. You interfere every cell phone, every computer, every facility. So this is only can be used for low power, but not high power. High power, you still need to use two stage and use current average, not discontinuous current. So we discussed about power factor correction. So if you measure in power system, then you can go back to think, what is power factor correction? You say, I use capacitor to remove the Q. So I can put capacitor, right, to improve power factor. But this is old idea. Now we use power electronics, so our current is not pure sinusoidal current. Our current has a lot of distortion. Then power factor has another definition. It is cosine theta multiplied by distortion factor. So you have to redesign the power factor correction. You cannot use only capacitor, because capacitor value cannot change. The load is always changing. But if you use a fixed capacitor, how can you obtain very good power factor at different load? It is impossible, right? Because your load is always changing. So in order to design the PFC, how many types? 2 types. One is for high power. So we use spatial transformer to design multi-pulse power factor correction. So which company has more patent? we call ABB, because ABB focus on high power. So they spend a lot of efforts in developing the high power factor correction. If you want to use the circuit, you have to buy the patent. Then you have to pay. So only some country they can manufacture this kind of circuit. You cannot copy it because they apply for intelligent property. The other side is active power factor correction. It is used for computer, used for cell phone, small power. Then we can use MOSFET. And also we need a lot of control, a lot of sensing. So the only problem is how can you simplify the circuit and reduce your cost but get the same performance. So this is the good opportunity. So I think we can finish the AC to DC converter, and we will have 10 minutes break, and after that we will discuss about the AC to AC converter. Okay, we have 10 minutes break.